Okay, hello everyone. Okay, how did the practice problems go? Did you guys have the chance to do them?
I did. Are we gonna be going over any or like?
If you have, yeah. Today, yes, I will. So if you have any questions, just go ahead.
Okay. Can we just go over some like the cardinality ones?
Oh, did I assign those?
Yeah, I think so. I think it was in the 2.3. Let me see. Yeah, it was 2.3 from 9 to 12 or about cardinality.
2.3. Oh. Assigned the wrong homework. Give me 1 minute. Section 2.3 is, what is it about? Is it about subset?
Let me check. I believe so. I think that's what it was called. I'm scrolling down to it now.
But it seems that I have a different copy of it. We have 1 minute, so don't worry about it.
All right.
Is it 2.3 or 2.4?
Oh, wait. I think I was in the wrong. Never mind. I think I don't know how, but I think I like was looking at the wrong.
That's okay. Don't worry about it.
Yeah. All right. Thank you. Sorry.
Don't worry about it. Okay. Any other question from anybody else? All right, Chris, can you go over number 19 and 22 for section 2.1? All right. So I hope I have the same section I gave you, 19. All right. No, sorry, it's 18 and 22. All right. So I will write up 18 and you guys will tell me what shall I write. So make sure I get the wrong version of the book. Write each of the following sets in set builder notation. So I have the following. It's a 0, it's a 4, it's a 16, it's a 36, 64, 100, ... etc. Okay. So we have to write this in set builder notation. Usually the idea is to see the pattern. I mean, what pattern is really going on. So go ahead. You guys take the stage. What pattern do you see? Okay, we have to rewrite this into a set builder. So we saw 2 ways of writing something into set builder. You will have the choice to pick the one you want. What's the pattern going on here? Don't make me pick. Go ahead, talk.
The first thing I noticed was that they were all perfect squares.
They are all perfect square. That's really the whole story. So let's rewrite it. This is 2 square, 4 square, 6 square, 8 square, and so on and so forth, right? So absolutely, and this is 0 square. Okay, so how can we write this in set builder notation? You can either write first the form of the expression and then the restriction on your variable, or you can write the domain and then the conditions that you want the element to satisfy. You have any idea?
I had it as x squared plus 2 such that x is an n.
X squared plus 2?
Yeah, such that x is an element of n.
Okay, let's see if it works. Let's see if it works. And then you fix yourself. You fix your mistake. Okay, it means all the term has the form x squared plus 2, where
wait.
x is an n. That's what you're telling me, right?
Yeah, but now I see my mistake.
Yeah, because if x is 0, you're gonna get
Right.
2. There is nowhere in sight. So fix
Right.
it.
Is
Fix
my
it.
mic working? Hello?
What?
Can you hear me?
Yes, very well.
All right, okay. So I have 2 times x squared such that x is in z plus.
2 times x squared. So I'm going to write each one of them, and then you guys will have to tell me. So this we decided is wrong. Do you understand why? Because only x equals 0, according to this set builder notation, we're going to have 0 plus 2. But 2 is nowhere in here. So this is failing. This one. Is this one working? Also, I don't know. If x z plus, it means z plus is everything bigger than 1. So if x is 1, I will have 2 times 1, which is 1, which is 2. 2 is not in my set.
Oh yeah.
Are you with me? I check what you guys
Yeah.
Yes, keep going.
Okay, it works after that. Okay, I didn't even look at the first game.
Whatever. All right. Who has another suggestion? Sorry.
I had 2n and then I squared that.
2n.
And then all that squared. And then n is in n.
Okay. Let's see if she's right now. Okay, if n is 0, we're on the right track. If n is 2, sorry, if n is 1, so that's give me 2 squared, which is 4. If n is, 0, 1. If n is 2, of course, she gets 4 squared. Absolutely correct. Because they are complete, they are perfect squares, but they are the perfect square of the even numbers. So that's why she get the 2n from, and they are squares of even number. That's why it's 2n squared, and this is absolutely correct.
For the sake of our class, are we including 0 instead of natural numbers? Because I know sometimes it's like.
Yeah, for our class, because I'm using the book.
Okay.
Yes, for the natural number, I am including 0.
Okay, because sometimes it's just they notate it differently.
Yes,
So I want to make sure.
Yeah. You're right. You know, there's always issue with that. So in the book uses 0 as a natural number. I'm gonna use it. So we will, yeah, absolutely. Z plus is set, but I am excluding the 0. So you guys will have the possibility of using either one of them.
Okay.
Is that this one clear? Any questions about that? Anybody has any other suggestion? All right, move on. Number 22. So every time you write something in set builder notation, you have to go backward and ask yourself, you know, do they give me the same element? Do they give me the same element? That's crucial. All right, number 22, let's see what it is. Number 22 is a bit tricky, quite tricky. So I'm gonna write it here. And I'm gonna put 21 here because somehow they are related. So 22, it's a 3, it's a 6, it's in 11, it's in 18, it's 27, it's 38, etc. And 21 is a 0, it's a 1, it's a 4, it's a 9, it's a 16, 25, ... Okay? All right, 21, tell me what you guys got quickly.
I got x squared.
That's honest to goodness x squared. All of them are perfect square, absolutely correct. Where my x is
An n.
Okay, 22. It's a little bit tricky. Let's see if any of you was able to figure it out.
For 22, could you do x squared plus 2 and then have it x in the natural numbers and then restrict it so x can't be, or x has to be greater than 0?
Exactly. This is going to be, as I said, a little bit tricky because you have to notice what's happening here. The 27 is 25 plus 2. 56 plus 2. 16 plus 2. I guess you know where I'm heading. 9 plus 2. 4 plus 2. And 1 plus 2. Now the pattern is, as your classmate said, absolutely correct. It's a perfect square plus 2. So that's the form of the expression, such that, what is my n, my variable here? Because I'm starting at 1, is in z plus. Okay. Or if you want, it doesn't really matter, you can put n squared plus 2, n in n, and n different from 0. Okay. Any other questions before we move on?
Yeah,
Go ahead, quick.
number 9 on 2.3.
2.3, number 9. Okay, this is again, so number 9 on 2.3. Okay, here they are giving you the set in set builder notation, and you have to list. So let us see, it's all the x's such that x is a subset, remember that means a subset of the set 3 to 1, means 3 to a, and so it's a subset of that, and its cardinality means the number of elements has to be equal to 2. Okay, so I want to write this, I want to list the element. So I have a set now. I immediately put the braces because I'm talking about a set, and I'm going to list the element in here. I don't know how many there are. Okay, so question number 1, what object are the element? What type of object? It means, are they humans? Are they letters? Are they, what are the object? What type of object are the elements here?
Sets.
Absolutely, set, and that's crucial. That's the type of object they are. So they are sets. So the elements themselves are sets because all the x's, such that x is a subset. So the element, what type of object they are set. Of, so they are set, and basically they are subset of this. And what they satisfy, their cardinality is 2. So give me one element in here. And then we can list all of them. Give me one, and then the rest will be simple.
The set 3, 2.
3, 2. That's one element. So watch carefully, we're gonna write it 3, because the elements here are themselves sets. That's one element. It's a subset of here, and its cardinality equal to 2. Now the rest will be simple. Another one is, of course, 3a. And this third one is 2a. Is there anything else? Any other subset of cardinality 2? I guess not. That's the proper writing. So this is a set. The elements themselves are subsets. So that's where those braces coming into the picture. And they have 2 elements in each. Okay. Any other question before we go on? Today it will be easy. It will be a bunch of definitions that I'm sure a lot of you are familiar with, but you have to work them out. Any other question before I move on? Okay, good. So last time we ended it by talking about subset, and let us remember the definition. So you guys will fill the details. So we say that A is a subset of B if every element of A is an element of B. If A is an element of B. That's where we did last time. Okay. And A is not a subset of B if, who would like to finish my sentence?
If there's at least one element in A.
If there is at least, exactly, if there is at least one element, at least one element in A that's not in B. That's not in B. Now, there is a fact that we will accept it, and at some point that I will actually tell you where it comes from, that we talked also last time about the empty set, which is a set that has no element. So we're going to accept the following set, that the empty set is the set that has no element, that we usually denote it this way, and sometimes you see people writing it this way, like braces, so there it's a set, but there is nothing in it. It's like an empty box. So there is a container, but this container is empty. Is a subset of anything. So whenever you have a set, it's a subset of every set. So the empty set is, we will accept this, is a subset of every set. So we write this clearly. So if A is any set, the empty set is always considered a subset of A. All right, so let me ask a simple question here. Okay, true or false, very simple. Suppose I have a set A, and the set contains the element 1, 2, and the empty set. It means I imagine A to be a container, because we imagine sets to be like box that have object that has a 1, it has a 2, and it has another container if you want, which is empty. That's what A is in our mind. True or false, the empty set an element of A. True or false, quickly. The empty set is subset of A. Okay, very quick question. The empty set an element of A, true or false? Quick. Rachel?
I say true.
Yeah, you are very reluctant. Why it is true?
I was muted.
Okay. Why it is true? Because it's one of them. It's right there. It's one of the object. So absolutely true. Is the empty set a subset of A? True, because I told you so. That's what you have to accept. Is the set that consists of the empty set, is this a subset of A? True or false? Tim, I don't know you, but Tim Backus, can you answer? If you don't mind.
Yeah, it's true.
It's true because
The empty set is in A, and like the actual empty set is in A.
yeah, it's in A, it means an element
Mhm.
of A, to be very precise. Absolutely true, because the empty set is an element of A. It means the set that consists of it is a subset. So what does it mean to be a set to be inside another set? It means every element here has to be here. The only element is the empty set, which is in A. So that's absolutely a true statement. Now, the set that consists of the empty set is an element of A, true or false? Logan, I also don't know you, Logan, but can you please share with us the answer? Logan, can you hear me?
Yeah, sorry. I muted myself again. I'm gonna say true.
Okay, if you tell me true, it means you're telling me that this is an element of A. It means it has to be one of those objects.
Yeah, it's the last one, isn't it?
Absolutely not. So this,
Okay.
no. Now, what's the difference between the empty set and the set that consists of the empty sets? Those are not different. Those are not the same. The empty set, you can imagine it a box that's empty, has nothing in it. What about this one?
Wouldn't the empty set have cardinality 0 and the other one have cardinality 1?
Absolutely correct. I will come in a second. How about this one? This
Yeah.
one is a set, but it's not empty. It
Right.
has
It
an empty box.
It have one element in it.
It got one element, which is the empty set.
Right.
So those two are absolutely different. And now, as your classmate said, the cardinality of this is 0. The cardinality of this is 1. Okay, so those are not the same creature. So, true or false? Is this an element of A?
Well, obviously false now.
What?
That it's false now.
Absolutely false. Yes, absolutely false. To be an element, it has to be one of those objects. It's none of those objects. All right? Okay, now we're going to define the following idea. Please, as I go on, ask me questions. That's the only way we can work. I mean, I don't want to be always asking questions. Please, you help me out. So we're going to define the idea of a power set. Power set. All right, so we have a set, any set. A, let us say 1, 2, and 3. Okay, and how many subsets does this set have? Does it have a lot of subsets? So suppose I ask you, give me list 4 different subsets of A. Okay. All right, so we have a lot of subsets. I want 4 of them. Who would like to give me one? Simon? Simon? Okay. Rachel?
The set containing 1 and 2.
The set that contain 1 and 2. Another one?
2 and 3.
2 and 3. Another one?
3 and 1.
3 and 1. Another one? I want 4.
1.
1, the singleton 1. Are there more?
Yes.
A lot.
There,
Yes, a lot. We can have 2. That's a subset. We can have 3. That's a subset. We can have the one I told you to accept, the empty set. That's also a subset. Who can give me one more?
the set containing 1, 2, and 3.
The set containing 1, 2, and 3. Do you think there are any other ones? That's the subset of cardinality 0 is only this. All the subset of cardinality 1 are 1, 2, 3. All those of cardinality 2 are 1, this one, that one. And then the cardinality 3 was to the set itself. So it has a lot of subsets. The power set is a new set whose elements are the subset of A. So power set, we're going to define now a new set called the power set. Definition, what's the power set? Okay, the power set, so let A be a set, B a set. Then the power set of A, the power set of A that we denote by, oh sorry, if I go offline, let me know. P of A, denoted by this, is a set. So it's we're constructing a set. So when I construct a set, I have to tell you what the elements are. It's a set whose elements are the subsets of A. It's a set whose elements are the subset of A. So if you have a set A, we can construct out of it a new set that we call it the power set of A, which is a new set. The element of it are the subset of A. So in this scenario here, when we start listing all the subsets, we're going to create a new set, and this new set, we call it the power set of A. So it's a set, we have the braces here, its element are the subset. So in set builder notation, how we represent the power set of A. Set builder notation, we can write the power set of A are all the S, but what is S? All the S such that S is a subset of A. Okay, one more statement. So what does it mean for S to be an element of the power set? Finish my sentence. So what does this mean? So whenever I define a set, you have to understand its element. What does it mean to say S is an element of the power set of A? What are the elements? The elements are the subset of A. So S is an element of the power set of A. This means that S itself is a subset of A. So let us build some power set and understand this idea. So we have a set, it has a lot of subsets. We create a new one whose elements are those subsets. That's what the power set is. So let us do some example. So example number one, let's just build them. Suppose A is the singleton one. So A is a set, it contains one element, one. Okay, what's the power set of A?
Would be the empty set and then the set with one.
Empty set is one of them. The set that consists of the singleton one. That's it. Okay, let's take another example, very straightforward. I already did 3 elements, 1, 2. What's the power set? Again, the empty set, because we accepted the empty set is a subset of anything. Okay, 1. So all the subset of cardinality 1, this one and this one. And then there is the set itself, because A is a subset of A. Every element in A is in A. So the other one is 1, 2. End of the problem. Now at the beginning, we took A to be 1, 2, 3. And we also computed its power set, which is all the subset, right? There is a fact that I will prove it very soon when I start working with how to count things, is that suppose A is a finite set, but this actually it helps us a little bit. Suppose A is a finite set. Then, if we know the cardinality of A, suppose the cardinality of A is n, then the power set, now the book has a proof, but I will show you the proof later on myself. Then the cardinality of the power set is 2 to the power n. So it's a very useful fact. So once you write the power, you make sure, are you writing it correctly? So let's check. In this case, the cardinality of A is 2. So according to that, the cardinality of the power set of A should be 4. 1, 2, 3, 4. We're doing fine. Here, the cardinality of A is 1. So the formula tells me the power set of A should have 2 to the power 1. 2 to the power 1 is 2. P of A has 2 elements. Okay, and the one I started with, 3 elements. Let's see how many we have here. So the formula tells me we should have 2 to the power 3, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's really it's a very useful fact, and it's helpful sometimes. Okay, let me now give you the following. Suppose A is the empty set. Okay, that's a set. That's the power set of the empty set. It's a set. What does it have in it? All the subsets of the empty set. When I am quiet, it means I want answer.
Would it just be the empty set?
It will be the empty set. Is there any other subset?
No, because it should be
Absolutely.
0. So 2 to the 0 is 1, right?
Right. So let's see if it follows the same fact. The cardinality of A is 0. So the cardinality of the power set should be 2 to the 0, which is 1. Absolutely. This set contains 1 element, which is the empty set. So let me ask you a simple questions. True or false? And then you justify. So we know what the power set is, or the subset. So suppose I'm taking, so that's the first question is fairly simple, 1, 2. Okay, and I take the singleton 2. True or false?
True.
True. If you say true, you should do what? Justify. If you say no, you justify. Okay, so I'll rewrite the question here and we'll discuss it. So my question is true or false? Subset of the power set of 1, 2. Remember what subset means. What does a subset mean? Every element here should be here. Okay, true or false? You said true, justify.
All right, so the power set would be the set containing the empty set, the set with 1, so with 2, and then itself, I believe, right?
That's the
Two
power
to
set.
the, yeah, so it's be a total of 4 different elements, and the one that is the set of 2 is, well, in there, so.
Nope. What's his mistake? Who can correct your classmate? But I don't know who, so we're fine. What's his mistake? So he said it's true, and I'm having issue with that.
Would it be an element?
Right, right. 2 is actually an element of the power set. Why it's an element? Why it is an element? Because it's this one right there. It's one of those objects. Why it is an element? Because 2 is a subset of 1, 2. That's why it is an element. So it is an element because what does it mean to say something is an element of the power set? It means it's a subset of it. So is 2 an element of this? And the answer is yes, because 2 is a subset of 1, 2. So element. Now, why this is false? Why false? Question mark. Who can give me a solid reason why this is false? Anyone? Anybody can tell me why this is false? Okay, suppose I tell you 1, 2 is a subset of 1, 2, 3. Is this a correct statement? Yes or no?
Yes.
Because every element here, what are the elements here? 1 and 2. 1 is in here, 2 is in here. So the reason this is a subset because every element is in here and this one is in here. That's what causes it to be a subset. Now, that's what subset means. So is 2 a subset of that? Why this is false? Who can really tell me why it is false? What are the elements of this set? What are the elements?
The element of that set's 2.
2.
And so then the elements of the power set would be the set 2.
Right, but it's 2. 2. Not the set 2. It's 2. an element of the power set? Is the number 2 an element of the power set? Yes or no?
No.
No, because the element of the power set are what? They are themselves sets.
Yeah,
so they are
sets.
boxes, they have stuff in them. They are not loose object. So every element of the power set is by itself a set. So it's just a box. There's a difference between an apple on the table and a box that have an apple. So those are two different objects. So is 2 an element of that? And the answer is no. Since 2 is not an element, it means the set that contains 2 is not a subset of the power set of 1. Okay, so the element of the power set are themselves collection of stuff. They are subset. 2, which is just a number, it's not one of those objects. So it's not an element of the power set. Because it's not an element, the set that contains it is definitely not a subset. All right. Who would like to give me a subset of the power set? So I want the following example of a subset of the power set.
Could you take like the bracket, like the set bracket, and then do another one with it around it? Yeah.
That's, now we're talking. That's a subset. And why? If I ask you to justify, how would you justify? Why is this a subset?
Because the element of that set is the set of 2, which
Yes.
is in the power set.
Right, because the element here is in the power set of 1. All right, that's how we justify. Now let us say I take the following, another simple example. Is this true or false?
True.
True, because we have 2 elements. This element is an element of the power set. This one is an element of the power set. Every one of them is an element of the power set, hence the set that contains them is a subset. So to check whether something is a subset, you go with element by element, and you make sure that each element is inside your bigger set. That's the inclusion. Belong, an element of, you just ask yourself, is it one of those? That's what an element is. All right, one more question about power set. And then we're going to construct another set. So my question is again a true and false. If I take the set that consists of the empty set, this set, is this an element of the power set? True or false? Okay, I would like to pick somebody. Emily. Emily.
Would it be?
Remember,
Would it be true?
Why?
Because it's an element of the.
What's this word?
Oh wait.
Wait, yes.
It would be false because the left side saying a subset, or the
Right.
set of the empty set.
Absolutely, that's false because the set that consists of the empty set is not an element. The empty set itself is, but not the set that consists of the element. Now, what if I write this? Is this true or false? Let's see if I can get, let me see somebody. Rachel, with me?
Yes, I'm here. One
Yes.
second.
It's true or false?
So that would be
Remember, that's an inclusion, right? That's a set and that's a set. What does it mean to say this set is a subset? It means you look at it element by element. You ask yourself, is every element in here? Now,
right. It would be true, correct?
yes, because. Don't be, yeah, because.
Because the empty set is an element. So when you
Very
take
good.
the set of the empty set, it's
Because
subset.
the empty set is an element, so the set that consists of the empty set is a subset. Okay? Very well. So the power set is a little bit confusing because we're putting set inside set, but we, you guys will eventually get a good hang of it. Now we're going to describe another set, which are also another important set, and it's a bit easier, but again, a crucial set in math, which is the Cartesian product. Sorry, this is section 2.2 in the book, and power set was section 2.4, I think. So Cartesian product. What's the Cartesian product? Before I talk about Cartesian product, I would like to talk about ordered pairs. So what's an ordered pair? We use the following symbol. So we use the following symbol. The symbol parenthesis A, comma, B, to denote, so this is parenthesis, and that's important now, to denote the ordered pair. The ordered pair. Okay, then that has A is the first term and B is the second term. So this is called the first term of the pair, and this is the second term of the pair. And two pairs are said to be equal. If you have two pairs, two ordered pairs, what does it mean for two ordered pairs to be equal? It means the first term here is equal to the first term here, and this term here equal to that term here. That's what it means for ordered pair to be equal. And we should not confuse, so be very careful. We're not supposed to confuse this and that. So the bracket and the parentheses mean different things. When I put braces, I am talking about a set of two elements. When I put parentheses, I'm talking about ordered pairs. So in this scenario, the order does not matter. But I'm talking about ordered pair, definitely we cannot change the order. Okay. Now what's a Cartesian product? So definition of a Cartesian product. So suppose we have two sets A and B. Suppose A and B are two sets. Then the Cartesian product. Cartesian, it comes after the name of the mathematician Descartes, or the philosopher. So the Cartesian product of A and B that we denote by A cross B. So A is a set, B is a set, is defined as follows. We define it in the following way. What is the Cartesian product? A cross B is all the ordered pairs, A, B, such that the first term is in A and the second is in B. Okay, so that's the Cartesian product of two sets. Definition that, believe me, you will encounter tremendously. So let us take example. So this is a new set we're constructing. the element of the set are ordered pair. So let us again see some examples. Suppose I take A to be the set of numbers 1, 2, and 3. That's it. And let B be the letters UV. Okay. Let us list A cross B. So I want to list all the element in A cross B. It means 1, 2, 3 cross UV. Okay, let's list this. What are the elements? What type of element? What kind of objects are the element of A cross B? They are ordered pair. This is type of object. Like the power set, the elements are sets. Here, the elements are nothing more than ordered pairs. So let us write this. So first, this is a new set. So we have braces. Let us list the element. All the ordered pairs. The first term in A, the second term in B. So you help me out because I may goof now. So 1, U, am I right? 1, V, 2, U, ordered pairs, 2, V, I try to write them in certain order, 3, U, and 3, V. And that's a set. So it's a new set whose elements are nothing more than ordered pair. So that's what we talk about, the Cartesian product of two sets. Now we can sometimes visualize the Cartesian product. So let us see an easy way to visualize it. I mean, the ordered pair, we always visualize them as point in the plane. But here I put U and V, but it's not going to be a big deal. I still will be able to visualize this. So we're going to visualize it like this. So I'm going to put A down here. So this is 1, 2, 3. So as you imagine, I'm really kind of imitating the plane. So here I can put B, which is U and V. V. So how can we visualize the Cartesian product? So it's 1 U. That's the point. That's 1 U. And then it's 2U, the second point. Then 3U. And this helped me make sure I'm listing them correctly. 1U, actually I did differently. And then you have this one, 1V, then 2V, and this one is 3V. Okay, so that's one way we can visualize the Cartesian product. And this also helps us to find the cardinality of the Cartesian. Now, of course, I can really count them, but what's really the cardinality in general? It's equal to what? To every element of A, I associate two elements of B in this particular scenario. Every element of A,
would it just be the cardinality of A times the cardinality of B?
it's going to be nothing more than exactly, and that's where the product idea coming from. It's just the product of the cardinality. Okay, because for each element in A, if I start with that, then I have here how many elements in B? The other element, how many elements in B? So what's going to be nothing more than the product of those two numbers. Okay, let's, and again, every time I do something, to practice it a little bit. So suppose actually I take this problem, fairly simple, and I ask you B cross A. Is it the same thing or very different? Am I asking the same question or not? Yes or no?
Yes.
Yeah, but the visualization would just, I guess if you would just flip it for the visualization.
For the visualization, flip it. Am I
Yeah,
asking
but
this?
it's the
Are
same-
they the same set?
It's the same points because you get the ordered pairs the same.
I agree, but are they the same set? Are the sets equal? What does
No.
it mean for two sets to be equal? Two sets are equal if they have exactly the same element. So will B cross A cross B will have the same element.
No, they would have.
Let us list them. U 1.
Yeah, no order pairs flip, so no, it wouldn't be.
Absolutely not the same set, because when is there U1 in here? And the answer is no, because ordered pairs are equal if the first term is equal and the second terms are equal. So there is no U1 in here. 1U and U1 are very different ordered pairs, because two ordered pairs are equal if they have the same first term and the same second. Those are very different. So this one is nowhere to be seen. So A cross B and B cross A are actually very, very different objects. So, and now I can keep going. U2, U3, V1, V2, and V3. Okay. All right. Let's play a little bit more with the Cartesian product. So how to write the term is easy, but let us work a little bit more with it. So suppose now I have the following questions. Sorry. I want you to visualize. First, let me talk about R. R is the set of all real numbers. I think we defined that, all real numbers. Okay. And I'm going to remind you a little bit the interval notation. Suppose AB, close bracket, this L, the X is in R, such that X between A and B. Okay. So with this in mind, I would like to visualize the following Cartesian product. 0, 1, cross, 2, 4. Okay, first, what's this? What's 0, 1, cross 2, 4? It's the set of all ordered pair, X, Y, such that X is in here. And Y is in here. That's what this product is. So it means is that that's the set of all X's Y, such that X is between 0 and 1, and Y is between 2 and 4. So in set builder notation, that's what this Cartesian product is, all the ordered pair that satisfy. So how can we visualize this in the plane? So this is the plane. Now, we can visualize this in the plane. What am I looking for? So this is R, of course, and this is R here. I'm looking at all the ordered pair that satisfy this condition. So can anybody tell me what is this? So 0, 1, I visualize it, this interval. That's 0, 1, everything in here this time. That's 0, 1. 2, 4, if I visualize it here, so that's the 2, that's a 4, that's 2, 4. Okay, and now what am I looking at? All the ordered pairs, X and Y. So that X in here and Y in here. So what do you think I'm gonna get? So if I take this point here, is this point in the Cartesian product? Yes or no?
No,
No, because
it's not in either. It has to be in both of the regions.
it has to be in
part
both
of
of the regions.
of the
So this
Cartesian
is
product.
this is outside. If I take a point here, is it in the Cartesian product?
No.
Because so if I take a point here, -1, 2, is this in the Cartesian product?
No, because it's not in 0, 1.
Right, because this is not in. So which are the
yeah.
point? Okay, because the X has to be in 0, 1. So that's not in the Cartesian product. Okay, a point here, no, a point, yeah, a point right here. So let us say this point is what? This point, I'm making it up. Let's say 3 from here and 4. Is this in the Cartesian product? No, because which one is not satisfied? 3 is that the y is satisfied, but x is not in 0, 1. It means it's not in the Cartesian product. So which point will be? Every point where the x is in here and y in here. So the x has to be between 0 and 1. And the y has to be between 2 and 4. That's my y should be. So every point should be in this region because that's the x, and it should be in that region. So the Cartesian product, we can visualize it as this box or this rectangle. Okay, and very important realization, because a lot of time the way we would describe a square or a rectangle in R2 is as a Cartesian product of two intervals. So that's really the way we can visualize this Cartesian product.
So just from looking at the visualization, it seems like the Cartesian product kind of sets the boundary for the points. Is that
What I
normally?
give you, it depends on this, what I give you. I cannot answer this question because
Okay.
I can really play around with that.
Okay.
Okay, I'll give you another example where you think I can really play around with that. But this is, if this is an interval and this is an interval, this tells me that the x has to be in here between 0 and 1. And the y has to be in here. And so the point has to be in this box. That's how we visualize it. Okay, let me take one more example because we have a little bit difficulties with that. So I would like you to visualize the following. So I take another piece of paper and you're going to visualize that. Very simple, no, not simple, sorry. Very, suppose let me take the following Cartesian product. 1, that's my first set, and the Cartesian product with z. You know what z is? Okay, let us list the element. Who can give me one element in this Cartesian product? Get going. Tim. Tim, are you with me?
Yeah, -1.
-1, is this an element in the Cartesian product?
Oh, I'm sorry, 1 -1.
1 -1. Because every element is in ordered pair. That's correct. Who can give me another one?
1 0.
1 0. Who can give me another one? Can we list all of them? The first is always 1 because the first entry should be in here. It means the first entry can be only 1. The second entry can be any integers. So 1, 2, 1, 3, and so on and so forth. 1 minus 1, 1 minus 2. And this is what we are talking about. So this set, this Cartesian product, actually it's a way to represent those ordered pairs. So that's going to be graphically. Can anybody? So every ordered pair, we're going to visualize it as a point in the plane. That's the best, easiest visualization. So if I want to visualize everything in the plane, how can I visualize this Cartesian product? Vertical line, absolutely correct, because the first component is always 1. It's not quite a vertical line. I'm having a little bit issue. Is it the whole vertical line? 1 0, 1 1. I'm not allowed to take anything in between. 1 2, 1 3, 1 4, 1 5, and so on. And so on and so forth. Since they are dotted, I cannot connect them because my second component has to be an integer. It cannot be just a real number. So this, we can visualize this as this vertical line, but not the whole vertical line, only the dot on those vertical lines, where the second coordinate is always an integer.
So if it was in R, like in all real, it would be just a normal line.
Exactly.
Okay.
If I change, the minute I change my universe, my sets, The minute I put it like this, you're absolutely correct. Then I'm gonna pick up the whole line.
Okay.
I can keep playing the game. I can put 1 and I can cross it with the interval 2, 3. How will this affect the picture? So here I'm taking all the ordered pairs, x, y, where the first is 1. That's the only value I'm assigning to it. But what about the second one? It's between 2 and 3. So what will I get in this situation? What will I get in this situation?
Would it be a line at
Augmented?
x equals 1 going from y2 to 3?
Yeah, I will have the following. Not the whole line. X is 1, it means the x component has to be in here. But the y is between 2 and 3. If this is 2 and this is 3, my y has to be from here to here. That's where my y should be. So what's visualization is this line segment. From here all the way here. And it's everything included because that's our definition for time interval. Okay, that's how we can visualize this Cartesian product. Any other variation you guys want?
Just a quick question. So our first example was with integer numbers. When you write it with real numbers, how would you suggest listing it to suggest?
I will never ask you to list.
Okay, just because.
Absolutely not.
Okay, yeah, that helps. Just because.
Absolutely not, because there is one of the main theorem in mathematics is that you cannot list.
Right. Okay. Just making sure for.
Yes. Yeah. Absolutely not.
Okay.
Right. Please. You can list the rational, but we cannot list the integers.
Yeah. Exactly.
Anyway, so this is being said. We can generalize. Before I generalize, there is a notation that we also should know. So suppose A is a set as well, nothing more. Then sometimes we see A square. What do we mean by A square?
The A cross with itself.
It's just A cross itself. Okay? It means, what's A cross itself? It means a set. All the element has to form a, what should I write here? What do you want me to write? I want to write in builder, in set builder notation. What should I put here? Don't be afraid. AB, such that A in A and B in B. So A squared is nothing more than A cross A. With this idea in mind, a lot of you have seen R square. And all of us, we visualize R square is all the point in the plane. But what R square mean? R square mean R Cartesian product R. So that's really the definition of R square. It means, again, all the pairs, AB or XY, I don't care what you write, where A is in R and B is in R. Okay? Now, we can generalize the idea of Cartesian product. So instead of taking Cartesian product of 2 sets, I know I can take Cartesian product of 3 sets, of 4 sets. So let us generalize a little bit. Generalization. Okay, so what's the idea? Suppose I have A1, A2, etc., AN, BN sets. So all kind of set, n of them. Then we define a new set called A1 cross A2 cross A3. That's the Cartesian product AN. So how we are going to define this? In the most natural way. It's a set whose element, we call them usually n tuples. Okay, it means element have the form A sub 1, comma, A sub 2, etc., A sub n, where each one of those AI belong to that. So what do I mean by this? What do I mean by this notation? It means that if I write it more in details, all the n tuple such that A1 is in A1, A2 in A2, and etc. A sub n is in A. Okay, so we can generalize the idea of Cartesian product. So just to make sure we understand this a little bit, let us play with the following. So suppose I take the following set. I don't know. So I'm going to take A to be 1, 2. I'm going to take B. I'm not going to visualize now. We just have to make sure we understand this notation. Let's say this is 3, 4. And let me take C to be, I don't know, 1, 2. Let me make it smaller. C equal 1. Okay. And now let us list all the elements in A cross B cross C. But first of all, what is A cross B cross C? Let us remember define. It's a set. The element consists of 3 numbers. So A, B, and C. That's really what it is. Where A in A, B in B, and C in C. So the elements are triple. That's what the elements are. 3 tuple. Okay. So let us write this. So we have a lot of them. All right. Shall we list them?
Yeah, can we go with 1, 3, 1?
1, 3, 1. What's the second term?
1, 4, 1.
1, 4, 1. 2, 3, 1. 2, 4, 1. You can actually make a tree if you want. So I gave it, or you can build a tree. So at A has 2 elements, 1 and 2. And then for 1, you can associate the following element in B, 3 or 4, 3 or 4. And B, you can associate to it 1 element in C, 1, 1, 1. This way you can get all of them. So the element would be 1, 3, 1, 1, 4, 1, 2, 3, 1, 2, 4, 1. So you can sometimes build a little tree to be able to get all the elements. All right, what about the cardinality? The cardinality. The idea generalized. The number of elements is the number of element of A times the element of B times the element of C. So the same rule will actually hold, and this picture will show you why this rule is holding. Right? So, and this is helpful because it actually also gives me a hint that I'm getting all the numbers. In this case, A has 2 elements, B has 2 elements, so, and C has 1 element. So the cardinality of the product should be 2 times 2, which is 4, times 1, which is 4. We actually got 4 elements. So knowing the cardinality, a lot of time help us really at least to know that we have the correct number of elements, and then we have to make sure we have the correct element, right? So with this idea, what does R3 represent? R3 for us is R plus R plus R. So R3 is what we imagine R3 is. All collection of list of 3 numbers, where each one of them is in R. Then Rn is list of n numbers, where each one of them is in R. So that's what Rn is, but that's what R4 is, that's what R3. So R3 is nothing more than the Cartesian product of R by itself. And that's the definition, it's just set of 3. Right, so we finish today with the following question. Now the following idea, suppose I take the following interval. following interval. 1, 2, cross, oh no, actually, cross 2, 4, no, 0, 2, no, it doesn't matter, 0, 4, cross 0, 2. Okay, 1, 2, it means all numbers between 1 and 2. All numbers between 0, 4, all numbers between 0 and 2. So what does this set represent? So this is set, the elements are this stuff. So that's are the element. Such that x between 1 and 2, y between 0 and 4, and z between 0 and 2. How can we visualize this set? If I visualize every triple as a point in R3, so I visualize each one of them as a point in R3, how can I visualize this Cartesian product? Okay. The x has to be between 1 and 2, the y between 0 and 4, and z up to here. How would you imagine this? Anybody? Tim, Rachel, Nick, anyone? Emily? How would we visualize this in R3? X should be in here. Y should be in here. And my z has to go all the way up to 2. So how can we visualize that? We can visualize this, nothing more than a box in R3. Okay, so if I want to describe a box in R3, sorry, this goes all the way up to here. If I want to describe a box in R3, I describe it actually as the Cartesian product of 3 intervals. So my x between 2 and 4, my z go from here to, my y go from here to here, and my z go from 0 all the way up to 2. So that's the best way possible to describe an interval, not an interval, sorry, to describe a cube in R3. Is it making any sense? Yeah, it's a box, absolutely a box. All right. Okay, so I will stop today at this, with that. Next time we finalize the section about sets, and I will assign some practice problems. I was planning to give you a homework, but I think I was gonna just assign practice problem, and on Monday I will give you your first homework because we will be done with the section about sets. Okay. Any questions before we let go? You guys are too quiet for me. Any questions?
I don't think so.
Yeah, I got a quick one.
Go ahead.
So I'm new to the whole like online learning stuff. Do you have any of the old lectures posted? I missed the first one.
I have last time's lecture.
All right, is it posted on Bright or somewhere else?
Yeah, no, it's on Brightspace.
Okay.
Oh yeah.
Do you know what tab that would be by chance?
What?
Like like I said, I'm all new to the whole online stuff. Do you know where on Brightspace that would be?
Oh, yeah. Give me a second. Let's see if I can pull it for you. So just give me 1 second.
I think if
It's
you go
under
to
the
content,
recording of the lecture.
yeah, if you go to content, it should have it on the side, on the left side of the screen.
Yeah.
Viewer.
I'm trying to
Alright.
share the screen to see if I can give it to you guys. So this is my class. This is 348. This is the content. And in the content, I actually are gonna be putting everything. So that's the syllabus. That's the recording of the lecture. So you hit recording of the lecture, you hit on YouTube, and then you hear the whole lecture. And then here I'm gonna put this practice problems. So that's the practice problems that I assigned for last time. And And then
Okay.
today I'm gonna assign other practice problems. And on Monday, I start giving you homework. Those are the homework that you have basically to write up and then do them and hand them back to me. And they will be also put on Brightspace. I mean, here in the content area, that's where I put everything. And you guys will be also giving me your homework back. You'll upload them into Brightspace and I will grade them using Brightspace and I'll send you feedback. Does this answer your question?
Yes, it does. Thank you.
Okay, all right, so good luck, guys. Please go over the note, read the note. I know PowerSet gives the student headaches and Cartesian product, so they are not hard, but usually students have difficulties with them. So make sure you do the homework and try slowly to understand the material. And I have office hours. If you guys have any questions, please don't shy away. Okay, all right, have a good weekend. Bye-bye, guys.
Thank you. Take care.